Welcome everyone to another episode on the Shannon channel. Today, I'm really happy to have someone from the family, from Rutgers, from the statistics department. Today, our speaker is Min Shu, and he's going to talk about a very relevant, what I think is a relevant and timely topic. It's about inference for the history of randomly growing trees.
All right, thanks so much, Celine. This is day 49 of the coronavirus lockdown. Thank you for having me here, for giving me a reason to shave for the first time in days. I think it's going to be an unusual talk for the Shannon channel. It's definitely not in your typical set of talks. That's the only bit of information theory in the talk, by the way. But it's a very fun topic. The joint work with Harry Crane, also in the statistics department at Rutgers. The motivation for the talk is to understand the source and the spread of an infection. This is two headlines from, this is actually a few weeks ago, but it's still very relevant, that in an infection, such as infectious disease in the coronavirus, people are interested in finding patient zero. But infection can be understood in a wider sense. For example, the spread of fake news on social media, you can think of that as also a type of infection. And because of very consequential elections coming up in the United States, I think that the second form of infection is actually just as important as the coronavirus. Okay. So we're going to view the infection as a network. To visualize, here's an example of a network. This is a network of sexual contacts in a United States high school. So they're very prolific. I hope this channel is PG-13, by the way. So this is a network of sexual contacts in a US high school. So you can see that aside from this big cycle in the middle, it looks approximately tree-like, which you imagine because one person infects someone else and they infect someone else and so forth. As another example, here is a network of both sexual contact and injection, so needle sharing, among a group of people in Colorado Springs. Here you see more cycles, but it's, I don't think anyone will fault me for saying that this is not that far from a tree. Now, in both of these cases, you can imagine that these people have HIV, and it would be, of course, important to know who was infected early to understand the spread of such a thing. Right? The problem I'm going to discuss is very intuitive and easy to visualize, but it does have a lot of technical definition. So before we drown ourselves in the technical definition, I just want to give the intuition. Here is the observed network of infections. Okay, so this is two nodes have a link if either one infected the other, but we don't know who infected whom. Okay, this is a network of 1,000 nodes, and the output that we want is a confidence set for the root of the infection. Here, the green nodes, there are 6 of them. They form an 80% confidence set. So we are 80% confident that the patient zero is one of these 6. And the cyan nodes, in addition to the green nodes, form a 95% confidence set. So that has 29 nodes. We're 95% confident that we have captured patient zero. This is it. This is an easy way to visualize a problem. Okay. Now, let's get down to the actual talk. So talk will have 3 parts. First, we're going to carefully define the model and the problem. And we're going to see that defining the problem carefully actually has a lot of subtleties. We're going to discuss existing work quite a lot. And then we're going to discuss our approach. It's really a synthesis of many approaches. And then we'll end with some simulation and real data. The real data doesn't have actual coronavirus data yet. We're still working on that. All right, notation. So this is something that people hopefully already know, but I just want to put everyone on the same page. If I have 2 discrete sets, A and B, suppose they have the same size, we're going to say theta of AB is a set of all bijections from A to B. Okay. So T, little t is going to be a labeled tree. The V of T is a set of node labels. E of T is a set of edges. Of course, tree is a labeled graph with no cycles, and it's going to be connected. I should have wrote here. Tree, we're going to take tree to always be connected. Given 2 labeled trees, we can have what's called an isomorphism between them. This is just a relabeling of the node labels. Okay, so we say that pi is a bijection, pi of t is equal to t prime if uv is in E of t, if and only if pi u, pi v is in E of t prime. Right? Most of you know this. This is kind of belaboring the point just to make sure that everyone's on the same page. And finally, we have this concept of an unlabeled tree, which is an equivalence class of isomorphic trees. In this talk, it is important to distinguish a labeled tree from an unlabeled tree. So we're going to use the word shape to emphasize this distinction. When I talk about the shape, it's always an unlabeled tree. If I say tree, it's always understood to be labeled. Now we can define our model. The outcome space is going to be what's called a recursive tree. So we say that a tree with n nodes is recursive if the labels of the node is 1 to n. So sorry, this bracket n notation means 1, 2, 3, 4, all the way up to n. Okay. So a tree is a recursive tree if the nodes are labeled with integers, and if any path from node 1 to any other node is increasing in its node value. So here we see a picture of a recursive tree, right? So you see that the path from 1 to 6 is increasing in node value, right? So if I were to swap 3 and 6, it would no longer be a recursive tree. We're going to define curly TNR to be the set of all recursive trees. Finally, we can define a probability distribution over a sequence of recursive trees, right? So we're going to call these capital T1, T2, Tn. It can be an infinite sequence. So we say that this is a Markov growth process if there is a transition kernel that tells you how to go from a tree of n nodes to a tree of n plus 1 nodes. Now that's just one additional node, and because it's a tree, we just have to figure out where to attach that additional node, right? Because every node just has one edge to the existing tree and possibly one edge to a future tree. So all we need to do to specify the transition kernel is we just need to determine where to attach node n plus 1. Okay. A famous example of a Markov growth process is what's called preferential attachment, where remember the question is, all we need to do is given a new node, we want to figure out where to attach it. And preferential attachment says that we're going to attach it as a function of the degree of an existing node, where the function is some phi. Okay, so I'll give examples of phi in a minute, but let's just visualize this. Here I have T6, this is a tree with 6 nodes, and I'm at iteration 6, so I want to include this unlucky number 7 into this. So unlucky number 7 is going to get infected. The only question is, who gets to infect node number 7? It could be node number 5, and that's going to occur with probability phi of 1. So it's 1 because node 5 has degree 1, normalized. It could also be node 1. It's 4. Now the numerator is phi of 4 because node 1 has existing degree of 4, right? It could also be node 3, which has an existing degree of 2. So the numerator is phi of 2. And you just pick one. What are some good examples of phi? The most classical is phi of d is d, so it's the identity. This is called linear preferential attachment, and this is what gives you the famous power law distribution of the degree. But you can also take phi of d to just be a constant. This is called uniform attachment. This means that you just pick an existing node at random to attach. You can also take phi to, as d increases, you can take phi to decrease. For example, you can take it to be the maximum of 0 and some large constant d minus the degree. So this is what's called uniform attachment on a d-regular tree. So imagine an infinite d-regular tree, and the infection has to take place on that tree. Okay, so everyone can only infect. So if d is equal to 3, that means that you can only, once you get infected, you can only infect 2 other people because you only have 3 neighbors in this background network. You can also take phi of d to be d raised to some exponent between 0 and 1. This is called sublinear preferential attachment. Okay. Just to show you some visualization, this is an example of preferential attachment where it's uniform attachment. Okay, so UA. And you can see that this looks quite different from linear preferential attachment, where you have phi of d is the identity here. Okay. All right. What is the data? So this is, I just defined for you this probability distribution, Tn, right? So the random recursive tree. But of course, that's not our observation because that has all the infection information. Instead, we observe the unlabeled tree, the shape of Tn, right? And through the course of this talk, we're going to need to refer to the specific nodes of the shape, but we know that the shape is the equivalence class. So just to be definite, we're going to let UN be an arbitrary alphabet of n elements. Doesn't matter what they are. And we're going to let T check be an arbitrary labeled representation such that the nodes are labeled with this alphabet. And for convenience, we're also going to define T curly T tilde n to be the set of all trees labeled with this alphabet. The alphabet is arbitrary. So we're going to take the observation to actually be Tn check. It's just an arbitrary labeled representation of the shape. I know that I'm belaboring the point, being a bit pedantic here, but it actually does become important later on. Now, because the choice of the labeled representation is arbitrary, of course, we have to make sure that our problem formulation and algorithm do not depend on this choice, this arbitrary choice, okay? I'm not going to verify this every time, but just trust me that this is the case. All right, with this definition, now we can define the problem of a root inference, okay? Let's just look at the picture first. So this is this Tn here is a true infection history. We observe Tn check. So what is a root in Tn check? Of course, it's B because 1 maps to B, right? So if rho is an isomorphism that maps Tn to Tn check, then row of 1, because T1 is always 1, row of 1. So row of 1, remember, is just the element in your alphabet. That is going to be the root node. So the problem of root node inference is to, for a given confidence level of epsilon, I want to construct a set, it's a subset of the alphabet of nodes based on the observed tree Tn check, such that the root is a member of my confidence set with probability at least 1 minus epsilon. Right. So it's, in this case, the C epsilon is going to be a subset of these 6 nodes, such that node B is in there with high probability. Well, it's not always going to be node B, right? This is a random event. A few quick remarks. One is, why did we jump straight to inference? Why not consider estimation? Well, it turns out that it's not that hard to convince yourself that under preferential attachment, at least, consistent estimation is impossible, right? Because when you just have 2 nodes, it's impossible to determine which one came first. Equal probability either way. You cannot do better than 50%. And the second remark is coverage of, so this probability guarantee, of course, is important criteria, but we also want the confidence set to be as small as possible. A trivial confidence set is to just throw in every node, right? That's definitely a valid confidence set, but we want the confidence set to be small. Now, before we go on, there's a technical issue that I want to address here. It's a little bit annoying, but it turns out to not be a problem for us. The issue is that the definition of the root node actually depends on the choice of this isomorphism rho. Take the picture I've shown here, right? There's many ways to actually have an isomorphism from the recursive tree Tn to the observed tree Tn check. For example, we can take the blue isomorphism, where node 1 is mapped to A, node 4 is mapped to D. Under this isomorphism, A is a root node. But we can have another isomorphism where node 4 is mapped to A and node 1 is mapped to D. Now, under that isomorphism, D is a root node. So this is annoying, but this occurs because, in a sense, label A and D, that doesn't matter. If you just look at the picture of Tn check, A and D are really indistinguishable nodes, right? And we're going to, this turns out to not be a problem. The way we'll bypass it is by saying that we require our confidence set to be labeling equivariant, in the sense that if you arbitrarily relabel all the nodes in Tn check, the confidence set gets relabeled in exactly the same way, right? So that this tau, which is another labeling, it's an isomorphism that maps from UN to UN. It commutes with the confidence set, right? So if you relabel the trees, the confidence set essentially contains the same nodes. They just get relabeled as well. So you can check in this case that if tau of T check is T bar, so you can imagine T bar is equal to T check, so that tau is what's called an automorphism, then row 1, so this is the root under one isomorphism row, is in your confidence set if and only if any other plausible definition of the root node is also in your confidence set. Okay, this is just a fancy way of saying intuitively, if a node is in the confidence set, all the nodes that's indistinguishable to that one has to also be in the confidence set. Okay, so when you include one, you have to include the whole family. If you exclude one, you have to exclude the whole family. So we can bypass this problem here. Good. So in the same way, we can actually define a more general inference problem. It gets a little bit abstract. So let's just jump to a concrete example here. So let's say that I fix a single node U. Okay, so let's look at the second example. Remember, a node is just a member of the alphabet. We want to know when was this node U infected. So you can think of this also as arrival time of node U. So in this case, we're going to define the arrival time to be the minimum from 1 to n, so this k here, such that U is a node, is a member of this tree row of Tn. Remember, row is any isomorphism that takes Tn to the observed T check, right? This is row right here. So you can imagine building a confidence set for the infection time of a node. That's a well-defined problem. And in exactly the same way, you can use the notion of labeling equivariance to show that the choice of the isomorphism actually doesn't matter here. All right, we're going to focus primarily on root inference. So let's look at some existing work on root inference. And there hasn't been that much work on general inference problems. Most of the existing approach to root inference takes this general framework that I presented here. So if you take any, so Tn check, remember, is our observed labeled representation, is arbitrary. Okay, we're gonna have a scoring function that's going to look at every node in Tn check and it's going to assign it a non-negative weight. And what we're gonna do is gonna sort the nodes in Tn check, and we're just going to include the nodes with the largest score. So that the question here is, how many nodes should we include? So then there's this function, k of epsilon, where this is a size. Now the three important results here, two of them from Sebastian Buback, Luc Devroy, Gabor Lugosi, one of them from Justin Kim and Pauline Lowe, who I think are actually in the audience right now. The first result says that if the random recursive tree has a uniform attachment, right, then so long as you take k of epsilon to be a function of this form, so a and b are just universal constants, then you're going to have that the confidence set contains a root node asymptotically with probability at least 1 minus epsilon. So this guarantee only holds as n goes to infinity. But what's really interesting here is that the size of the confidence set does not increase with the size of the tree. So even if you have a tree of 20 trillion nodes, so long as you give a confidence set whose size is at least k of epsilon, you can capture the true root node. Now, I haven't given you examples of the scoring functions psi, and I will in a second. But the theorem says that there exists such a psi, and that such a psi is computable. Okay. The other results are similar, except it's for other distributions on the random recursive tree Tn. So if Tn has a linear preferential attachment, then k of epsilon is going to be a function of this form. Okay, so it decays much less gracefully with epsilon. So as epsilon is small, k of epsilon, of course, has to be large. And then in the case of d-regular uniform attachment on d-regular trees, k of epsilon has yet another form here. I also want to mention one other additional kind of seminal work on this that we used a lot is Devereux Schott and Tauhid Zaman. They consider the problem of estimating the root on the uniform attachment on k-regular tree. So not for inference, but they actually devised quite a lot of the algorithms that we're going to use. All right. And I also want to say really quick is that Sebastian Buback and co-authors actually also provide lower bounds on k of epsilon. Okay, so but I don't want to go into detail on that. What are the issues? So these results are beautiful, right? For the reason I discussed before is that the K of epsilon does not increase with N. That's kind of surprising. But they do have issues. In particular, they're not practical. Why are they not practical? Well, first, the coverage is asymptotic, requires N going to infinity. This is not such a big issue. Asymptotic coverage exists all the time in statistics with CLT, right? Another issue is you need to know the model specification. To determine the correct size for the confidence set, for example, I need to know if Tn is uniform attachment, or if it's linear preferential attachment, or it's uniform attachment, right? That determines what K of epsilon I'm going to use. That's also not a huge problem. Right? Maybe you can imagine estimating that. But the most important problem is that these bounds are just too large, right? These universal constants, even if you work really hard to get a good estimate of the universal constant, these bounds are just going to be impractical. And I'll show the examples of these. In this talk, we're going to address, essentially, we're going to address all three issues. So we're going to have finite sample coverage within a class of a family of models. We're not going to require that you specify the model. So the confidence set is adaptive, and that the confidence set that we produce indeed are actually practical. Now, I still owe you an example of the psi function. So let's go back to this framework, right? This remember how these confidence set works is you have a scoring function for every node, and you just take the nodes with the largest score. The best scoring function is a likelihood. And here, the likelihood is actually not all that easy to derive. So without showing too much of the technicality, I just want to briefly describe what is a likelihood here and why the likelihood is actually kind of a difficult object. So suppose I observe Tn check, and I want to know what is the likelihood that a specific node U is a root, right? Well, first we're going to have this notion of a rooted shape. So I've given examples of this, right? So you observe a shape, which is an unlabeled tree. I can single out a node and I get a rooted shape. Okay. So once you have the node U and you have the observation Tn check, that's a rooted shape. So the question here is, among all the recursive trees that possible, right? Because the outcome is recursive tree. Let's take the set of all recursive trees that gives me a specific rooted shape, and I'm going to sum over all that probability. That's my likelihood. With one caveat is I talked about how nodes can be indistinguishable. So that's a set of this, what I call equivalent set. So this is a set of all, for a node U of a tree, this is a set of all node V, such that if you imagine dangling the tree at node U, and then you dangle the tree again at node V. If they give you exactly the same tree, we call these nodes exactly the same shape. We call these indistinguishable. Okay? So you can see that this is not an easy thing to compute, right? Like, let's take this rooted shape S double prime here. There is only one distinct recursive tree that gives you this shape, and I've shown it here. You cannot swap, if you just swap 3 and 4, it's the same recursive tree, okay? So there's only one. And you can imagine that as a tree gets large, this quantity it becomes difficult to compute. And indeed, what Buback and all says that, the co-author says that it's computationally intractable to compute the likelihood. So they consider relaxations. In particular, one relaxation that they consider is called product of subtrees. As an immediate consequence of this work that we have actually, we're going to show that actually, even though the likelihood is not computable, the MLE is computable. And in fact, this relaxation that they use is the exact MLE. It's going to induce the same ordering of the nodes as this likelihood. Okay, so that's one thing that we'll get to. All right, what is our approach then? So we're going to use two things. One is label randomization, and one is shape exchangeability that we'll get to in a second. Okay. The concept is really simple. So remember what our data is. Our data is Tn check. It's some arbitrary labeled representation of the observed shape, right? What we're going to do now is we're going to generate a random isomorphism, big pi, capital Pi. So it's random, uniformly generated from the set of all bijections from UN to UN. And we're going to define another random tree, Tn tilde, where we randomly relabel the nodes of Tn check. You can see that that's just capital pi composed with rho applied onto the original recursive tree Tn. Right, so now capital pi composed with rho, that's just a random isomorphism that maps 1 to n to un. Right, this is also a random isomorphism. For every k from 1 to n, I'm also going to define tk tilde, so that's the subtree of Tn tilde, to be this random isomorphism applied onto tk. So how you should visualize it is you're basically taking all the subtrees of tk, 1, 2, 1, 2, 3, 1, 2, 3, 4, and you're taking that part chunk out of Tn tilde. Okay, so this is going to give you a sequence of subtrees of Tn tilde. And I want to emphasize that Tn tilde, the node labels are un. So this curly T tilde n is just a set of all labeled trees whose labels are un. That's all it is. Okay. Just to make this more concrete, remember preferential attachment. Okay. What is a distribution? So we know what the distribution of Tn looks like, this random recursive tree. What does a distribution of Tn tilde look like? Well, it's basically the same. The only thing that changes is the random label. So in a sense, we're not changing anything at all, right? So T1 tilde, instead of being a single node with label 1, it's a uniformly random element from the alphabet un. And then at every iteration, instead of taking the new incoming node to be labeled T, where T is a current iteration, we're going to choose an alphabet from the uninfected set uniformly at random. So it's just the same, except the labels are random and it's from this set of alphabet un. Okay. So now, this is an important slide with the definitions here. The key here is given these randomly labeled trees, Tn tilde, we can now define a conditional distribution over, so what are we conditioning on? We're conditioning on the final observed tree, okay? So that's, if you fix any little Tn tilde, we're conditioning on that the big Tn tilde equals little Tn tilde. And we want, what is this conditional distribution over? This is a distribution over all possible subtrees, sequences of subtrees of Tn tilde. And we're going to define all possible sequences of subtrees to be what's called the history of a specific label tree Tn tilde. Okay. Another way you can view the history is just as a sequence of labels. So what I can do is I can just, what are my labels? My labels is just the alphabet un. So I can just lay out, I can just have a sequence of these labels such that if you take the tree restricted to any initial part of the sequence, it has to be connected. So these are just equivalent ways of looking at the history. So you can think of the history as just a sequence of subtrees, or you can look at the history as a sequence of nodes that obey this connectivity constraint. Right? And this conditional distribution is a distribution over the history. This distribution looks complicated, and it's not clear that this is helpful yet because we don't know if it's computable. But let's set aside the computation issue for a second, and let's see how this can help us with the inference problem that we discussed before. Okay, so let's turn to, oh, sorry, just a visualization really quickly. So now we had this really shape before, and let's take the tree. T tilde to be these 4 nodes labeled with alphabet A, B, C, D. So here we see that the history, so all the history starting with node A are these, starting with node B are these. So A has to follow B, right? Because I cannot have B, D, that's disconnected. C and D, etc. So the history does, the ordering of the nodes does matter in the history. Right, so you can see the history is a much larger class. Right. Let's go back now to the problem of root inference. So given that I have this conditional distribution over the history, I can now also define the conditional root probability. For a fixed label tree, Tn tilde, and for a fixed node, U in this alphabet, we can compute the condition. Well, I didn't tell you how to compute it yet, but we can, in principle, compute the conditional root probability, the probability that T1 tilde is equal to U, given Tn tilde is equal to this tree, literal Tn tilde. So let's say that we can compute this for every single node in this alphabet UN. Okay. A natural approach now is to sort the nodes in decreasing order of this conditional root probability, as I've done here. So U1 has the greatest conditional root probability, U2, etc. And now what we can do is, for a given confidence level epsilon, we're going to collect the nodes with the largest conditional root probability until collectively the conditional root probability exceeds 1 minus epsilon. Okay, so we include just enough such that we get at least 1 minus epsilon conditional probability. And so that's what this K epsilon of Tn tilde is. And then our confidence set is just B of Tn tilde. Now, some of you may look at this and you wonder, okay, well, this is like a Bayesian credible set, right? Another way to view this set is this is the smallest subset of the alphabet, such that the conditional probability T1 is in this set is at least 1 minus epsilon. And you know that this is not exactly the guarantee. This equation here, which follows by definition of B, this is not exactly the guarantee that we want. So the first of our results says that actually, indeed, a confidence set created in this credible set idea, this actually has valid frequentist coverage at any n. So this is for any n. For any random recursive tree Tn, if I create a set of nodes according to this procedure that I just described, using the Tn tilde probability, this is going to contain the true root with probability 1 minus epsilon. So even though this is a Bayesian credible set, the way it's computed, this actually has valid frequentist coverage. Okay. In general, this is not true. In general, Bayesian credible sets do not have valid frequentist coverage. There are many, many famous examples of this. Okay, in general, this is not true. What's special about this case is there's a great deal of symmetry in the way that we define these probability distributions, right? In particular, Tn tilde, if you just relabel the nodes in any way, you don't change the distribution. So the distribution is invariant to application of a relabeling. So this is what we use to prove this. And I didn't say this, but this is also labeling equivariant, that this set B epsilon of Tn tilde, this is a labeling equivariant confidence set. That's not exactly obvious, but it also comes from this. Looking at this theorem, what you can do is you can interpret this label randomization, this Tn tilde. This is not inherent to the problem, right? The problem is only over recursive tree and observed shape of the recursive tree. The problem itself doesn't really involve any random labels. So you can think of this as a augmentation of the data that we use to sort of help with the computation, right? But this augmentation, in some sense, is also intrinsic to the problem, which we demonstrate with our second result. And this is the one that ties together this conditional root probability to the likelihood that I just described. So let Tn be any random recursive tree, and let the T tilde be the corresponding label randomized trees. Then what we have is, for any label tree Tn tilde, the conditional root probability is equal to the likelihood normalized across all the nodes, right? Remember that the likelihood is just counting the number of recursive trees that results in this rooted shape. That doesn't involve any random label, right? That's defined completely without any random label. And in fact, that's equal to another way you can view this conditional probability, which is if I tell you that the random recursive tree has a certain shape, what's the probability then that it has a certain rooted shape? And you have to divide by the set of all equivalent nodes because you're only looking at a single node here. And this theorem says that these three quantities are all actually equivalent. So in some sense, this label randomization, it's an augmentation, but it's also intrinsic to the problem. It doesn't change the characteristics of the problem. Most importantly, it says that if you construct the confidence set in this way, this is an MLE. We are exactly maximizing the likelihood, okay? But it just makes it more computable. Now, we need to get to computation, right? We pretended all this time that these conditional probabilities are computable. But when is this the case? This is not always the case, you can imagine. And well, we formalize a notion under which this is easy to compute. So this is, we're gonna impose an assumption on the distribution of the random recursive tree Tn. We're gonna say that Tn is shape exchangeable if for any recursive tree, little tn and little tn tilde, so long as they have the same shape, they have the same probability. So that the ordering doesn't matter. The only thing that matters is a final shape. Okay, this is called shape exchangeability. So then it's very easy to show, actually, using the definition of label randomization, that so long as Tn is shape exchangeable, then this conditional probability over the history that we defined is actually uniform. Okay, so if the random recursive tree Tn is shape exchangeable, and if Tn tilde is the corresponding label randomized tree, where we apply random labeling to this, then the conditional distribution over the history, that's this quantity here. Remember that this is a distribution over the history, right? If you don't have a valid history, then clearly you have probability 0. That in fact, this is uniform over the set of histories, over all the sequences. Okay. So when is this the case, right? We just defined the shape exchangeability. Well, it turns out that the shape exchangeability applies fairly generally. So one of our results says that if you have the preferential attachment distribution with this arbitrary phi function, then Tn is shape exchangeable if and only if there exists alpha and beta such that phi of d is a maximum of 0 and alpha plus beta d, where alpha and beta has to satisfy one of two conditions. If beta is negative, then alpha has to be a multiple of beta. Or if beta is positive, then alpha has to be strictly greater than minus beta. So let's first take the case where beta is positive, right? So this includes linear preferential attachment. Take beta to be 1 and alpha to be 0. This includes uniform attachment. Take alpha to be 1 and beta to be 0. And in the first case where beta can be negative, this includes the case of uniform attachment on deregular trees, right? You take alpha to be big D, and you take beta to be -1. Because it's negative beta is allowed here. That's why there's a maximum between 0 and this quantity here. And finally, what about sublinear preferential attachment? Unfortunately, that is not shape exchangeable because this condition, this is an if and only if characterization. Okay, so doesn't have that, the phi for that doesn't have this form, so that's not shape exchangeable. And we'll discuss how to handle that case as well, how to handle computation for that case. Okay.
I have a quick question. So what is
yes,
the
of course.
behind shape exchangeable trees?
What is the intuition here? Yeah, so it's at the if I show you the final tree as a unlabeled tree, as a shape, it doesn't matter what the sequences I use to get there. What only matters is that only the final shape matters. So imagine that the final shape is a hub. Okay, it doesn't matter how the spoke came about. The only thing that matters is the probability depends only on the shape of the final observation. Let me see if I can find a picture to. Yeah, so let's say that in this case, what shape exchangeability says is 1, 2, 3, 4. So that's one possible recursive tree. 1, 2, 3, 4. That these two have the same probability because they have the same shape. Okay. And if you have, well, those are the only two possible ones that can give you this shape. But you can imagine that this is true for larger trees, so that the probability depends only on the shape.
Okay.
Okay. So this holds true for a family of preferential attachment, but it's not always true. But all you have to check is this if and only if condition that we have characterized. Okay, so it's nice to know that it's uniform, but how do you actually compute it, right? Because the set of histories, you can imagine, is still a fairly large class. Well, it turns out that this is easy to compute. Let's go back to, so let's go consider root inference, and let's go back to this quantity, this conditional root probability. Okay, remember that the conditional distribution is uniform over all history. So what is the conditional root probability? Well, this is just the number of history that starts at node U, right? Because everything is uniform. So you just have to consider all the history and look at the ones that starts at U. So it has this form. And this coincides with the notion of Ruber centrality defined in Shah and Zaman that I alluded to earlier, right? In particular, Shah and Zaman gives a very nice and simple characterization that allows us to count this history very efficiently. So here the notation is a little bit heavy, but the idea is very clear. So the idea is if you want to know the number of the size of history of a labeled tree T and tilde starting at U, what should you do? Well, what you can do is you can think of the tree, visualize the tree as being rooted at this node U. Okay, and now what you do is for all the neighbors of U, V1, V2, V3, you look at that subtree. So that's what I call this TV1U. So it's a subtree rooted at V1 where the whole tree is rooted at U. And you take their size is NVU. So you multiply the size of all three of these subtrees, and then you do it for subtrees of subtrees. Okay, so you do it at all the levels. So you take the product of these sizes and you do it at all the levels. And then you multiply all that and you divide, you take n-1 factorial and divide by that. And that gives you the number of history that starts at U. Okay. So far.
Hey, Min.
Yes.
Quick comment.
Yeah.
That equation, after I discovered it, I realized in Donald Knuth's computer programming book, he has that equation in there as like an example of calculating the number of linear extensions of a directed tree in a topological sort. So I didn't invent that. That was Donald Knuth.
Oh, okay. So that was Tauhid Zaman speaking. Thank you very much for Tauhid. Yeah, I'll also credit Don Knuth.
He did everything.
Well, later on, I call this the Shah-Zaman algorithm, but I call it the Shah-Zaman-Knuth algorithm. Anyways, so moreover, and not going too much detail here, using the fact that the number of history for a node for two adjacent nodes, there's a simple relationship between these. What you can do is you can have an algorithm. So I guess it should be Shah, Zaman, and Donald Knuth from even earlier. They have devised an algorithm that computes.
The algorithm is ours, man. He didn't do the algorithm. We did that.
Oh, okay. Okay. So this is Shah and Zaman. That computes all the counts of these histories for all the nodes in linear time. Right? And this is the best you can do, of course, because you're producing n numbers. And once you have this, of course, you can compute the denominator here very easily just by summing those up. In other words, what's the takeaway here? The takeaway here is that confidence sets can be computed in n log n times by using the Shah-Zaman algorithm and by sorting, right? These are the sorting that you need to do. Another thing is, notice that this confidence set, these quantities, they do not involve this alpha and beta in preferential attachment. So if you know that the preferential attachment model is of the form that phi of d is alpha plus beta d, you don't actually need to know what alpha and beta is to compute your confidence set. So if there was a statistical audience, I would say that that the shape of the tree is a sufficient statistic for the parameter alpha and beta. Okay. And finally, that this coverage holds for all finite samples. Okay, so there's no asymptotics here. All right, that was coverage. So what can we say about the size of the confidence set? Well, it turns out that using existing results from Buback, from Justin Kim and Pauline Low, and using the fact that this is constructed as a Bayesian optimal credible set, you immediately can get guarantees on the size of the confidence set. So if Tn is linear preferential attachment, uniform attachment, or uniform attachment on regular, irregular trees, then we immediately have that the size of the confidence set is OP of 1. So it does not increase with n. Moreover, you can bound the median of these sizes. So the size, by the way, is now a random quantity, right? Because it depends on the tree. For the original, for the approach by Buback and Kim and Low, the size is fixed. The size doesn't depend on the tree, but here the size is random. So we have that the median of the size is bounded by exactly these functions of epsilon that I showed earlier, right? And this is directly using their results. So that this confidence set, the size guarantee is exactly the same, at least in its dependence on the confidence level epsilon. All right, let's see these guys in action. So here's a quick example for linear preferential attachment. It's a node of 1000, this synthetic example. So the ones that has the red labels, that forms the 80% confidence set. There are 5 of those. And you see the labels right here. By the way, the orange node here is a true root node. Okay, so this is a lucky case where this one happens to have the largest conditional root probability of 0.3. And you can also build a larger confidence set. So here, the green nodes, it's hard to see them all, but there are 27 of them. They give a 95% confidence set for the root. Okay. And just as a comparison, if you were to use the bounds provided by Buback and co-authors, you get something that's not at all practical. But to be fair, their paper is more theoretical, right? They're not trying to, they're not trying to make something very practical. The achievement there is to show that this doesn't increase with n. But I would say that this is at least practical, that you can apply this and get practical confidence sets. Here's an example for uniform attachment. Again, the red labeled nodes here, there are 6, is an 80% confidence set. And the green labeled node, the nodes that are colored green is a 95% confidence set. So there are 13 and 6 and 13. And if you use the previous bound, you get 20 and 150. Right? So that's root inference. Now I want to talk very briefly about general inference problem. Remember that I talked about the inference on the arrival time, the infection time of a certain node. Okay. So in this case, what we can do is we can use Monte Carlo approximation. So we're going to consider the conditional distribution over the history. And let's assume shape exchangeability so that this is a uniform distribution. In this case, if I want to know the conditional probability of an event E, so in the case of root inference, this is the event that the first node, T1 tilde, is equal to U. So I can approximate this by drawing B, capital B, samples from this uniform overall history, and we can just take this Monte Carlo approximation. All I need to tell you is how to draw a sample from the conditional distribution, which is uniform, right? And we have the following proposition. This is probably known earlier. So if anyone knows that this result before, happy to attribute the credit properly. So this says that, so this tells you how to generate the sequence. First of all, to generate a history, I just have to generate a sequence of nodes that obeys a certain constraint. We already know how to generate the first node of the sequence by the characterization I've shown earlier, right? For root inference. This proposition tells you how to generate every subsequent node. So if I already generated k-1 nodes, this proposition says, in order to generate the next node, all I have to do is take the subtree rooted at that node, take the size. That's a probability proportional to which I should draw that node. Okay? So let's just look at this picture here. Imagine that this is a tree, and we already draw a node B, C, and D. What are all the possible nodes that we can draw next? Well, it's either F, A, E, or G, because it has to satisfy this connectivity constraint, right? So which one of these four should we draw next? Well, we should draw them with probability exactly proportional to the size of the subtree here, 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 and here. Okay, and they sum up exactly to this denominator. If you implement this naively, you get n squared, but it's very easy to implement it efficiently by modifying a random permutation in place. And here you can get a runtime of O of n log the diameter of the network. So it's at least n log n for one sample. All right, so let me just show you a quick example for the infection time inference. So on the left here, I have a network. I labeled 4 nodes. So yellow is a true root node. Green, red, blue are just 3 nodes that I labeled. And on the right here, what I did is I drew 500 samples uniform from the history. And I just plotted at what point did the red node enter? Was the red node infected? At what point was the blue node infected? And at what point was the green node infected? And here you see the conditional distribution of arrival time. So red node arrives very early. Blue node arrives early as well, but not quite as early as a red node. And green node, this is a leaf node on the periphery. So its distribution is definitely not in the first 50 nodes. You can't really see here, but this probability is very low. But the rest of the time is scattered, which makes sense, right? Because you can't really compare this against that node against that node. These leaf nodes are all kind of uniform once it's past a certain point. All right, and finally, I want to just talk really very briefly about what happens when you don't have shape exchangeability. When you don't have shape exchangeability, the conditional probability over the history is no longer uniform. But that's possibly okay, because we can use importance sampling. So what we do is we're still going to draw a bunch of samples uniformly from the set of all histories. And then we're going to compute the importance weight, which is this WB. So that's a probability of having the sequence. Under shape exchangeability, this is constant. This doesn't depend on the sequence. But when you don't have shape exchangeability, this typically will depend on the sequence. And under the assumption that this can easily be computed, and typically this is easy to compute because typically when you specify the probability model, you specify exactly how to compute this. We can still have our Monte Carlo approximation where we weigh each sample by its importance weight. Okay? So you can still use this. And the nice thing about this is that because the uniform distribution obviously dominates every other distribution, you can be sure that you might require a large number of samples, but at least this is you can do this for any model of random trees. Okay. All right. So that was summary of our approach. And now, very briefly, almost over time. Let's just look at some of the simulation and as well as a real data experiment. So in the simulation data, we have 3 knobs that we can tune. We can choose our model, we can choose the size of the tree, and we can choose the coverage level of Psilon. And we're going to look at 2 outputs, the coverage and the size of the confidence set. So in the first experiment, what we're going to do is we're going to change the model. So phi of d is going to be one of these. We have the theoretical coverage, and we're going to look at the empirical coverage. And you see that the empirical coverage lines up very well with the theoretical coverage, so that this is indeed giving you the right confidence level. Okay. Sorry, this is repeated over 200 independent repetitions. And now what we're going to do in the second experiment is we're going to change the size of the tree. So 5,000, 10,000, 20,000, 100,000. Okay. And the size of the confidence set, you see, doesn't really change. It gets bigger by a little bit, but negligible, right? Going from 20,000 to 100,000, the average size of the confidence set increased by 1. The next example is we're going to vary the epsilon, the confidence level. So in the first case, we have uniform attachment with 10,000 nodes. Okay. So if the confidence level is 0.9, so epsilon is 0.1, we get a size of 7.6. For 95%, we get 12.4. For 99%, we get 30. So if you were to use a bound provided by previous work, you get something that's not really that practical. And the situation is more dramatic with linear preferential attachment. Here we have a tree of 10,000 nodes. For confidence level 90, you get 14, 95, 35, 99, you get around 200. And the previous bound is just, it doesn't really apply for confidence level 0.99, right? And then but what you do see is you do see empirically that under uniform attachment, the size of the confidence set degrades much more gracefully with a confidence level, right? So as the level gets a lot higher, the size of the confidence set, it doesn't even increase by that much. Whereas the picture is much worse for linear preferential attachment. And that exactly confirms the intuition given in previous papers by Sebastian Buback and co-authors, right? They make exactly this observation. And here we confirm it empirically. And now, really quick real data experiment. So this is a set of flu transmission data from an epidemiology paper by Hans and co-authors from 2012. So this is showing the transmission of flu among 33 school children in Linden. Right? The true patient zero, and this is done through contact tracing, et cetera. They identify the true patient zero, that's this yellow node here. And we run our method on it. And both the 80% confidence set and the 95% confidence set capture the true patient zero. So these red labels are the conditional root probabilities. So you notice that the one with the largest conditional root probability doesn't have to be the true patient zero, right? And that's what we expect. And then we took a look at this paper deeper, and we realized that this is not really the ground truth. This is a best reconstruction provided by these epidemiologists. What is the real data? The real data is actually a network with cycles. It's this contact network. Here, the true patient zero is this yellow node here. Okay, so to test the robustness of our method, what we do is, let's say that the epidemiologist reconstruction was wrong, right? What if the true tree was something else? So what we did is we took 200 random spanning trees from this direct cyclic network, and we treated each random spanning tree as a random tree, and we perform our algorithm. And we show that we still get pretty good coverage. So at confidence level 85%, we get empirical coverage of 89%. At confidence level 95%, that includes 10 nodes, but that always captures the true patient zero. So this is where I kind of want to end, is that moving forward, the next step that we're looking at, of course, is to consider networks with cycles. And this idea of random spanning tree is kind of a good way to get at that. So hopefully that we'll be able to talk about inference on the history of a random growing network very soon. So with that, thank you very much for your time, and thank you, Celine, for having me again. Stay safe, and hope that this quarantine ends very soon.
Yeah, thanks a lot, Min. I think these talks are also meant to help us kind of tolerate, or use our times maybe in a beneficial way. Thanks again for the